Hey guys, the focus of this video is going to be on positive ion formation and also para and diamagnetic substances. We're also going to sprinkle in just a quick review of isoelectronic series and then also how we just write electron configurations for transition metals in the first place. So let's start with isoelectronic species. We introduced this the other day in class. Not sure we had an opportunity to take some formal notes on it, so I figured I'd slip it in now. Bottom line is these are species, which is kind of a generic term, atoms, ions, that have the same number of electrons and hence the same ground state electron configuration. So we'll see that in all 7 of these scenarios, whether we're talking about the neutral atom neon, or perhaps these anions or these cations down here, given that we've either gained or lost electrons, we all kind of settle on the electron configuration for neon at 10 electrons. Okay. Now we used these isoelectronic kind of series, these elements the other day, in the context of ionic radii to talk about how when we form an anion, those are going to be larger than their non-metal atom counterpart. And then when we have these cations, these are going to be smaller in size than their metal atom counterparts. Okay. We'll come back to isoelectronic series kind of throughout the course of the year, particularly when we get into the strength of ionic compounds, which has kind of a nice reinforcement of Coulomb's law as well. So with that in mind, as far as transition metals go, nothing super complex here. I mean, imagine we wanted to write the electron configuration for iron. We start kind of as we always would, right? 1s, 2s, 2p, 3s, 3p, 4s. The big thing is that, once you get to this fourth period, just recall that before you can kind of fill in that 4p, you don't get to 4p right after the 3s level. You got to attend to the electrons in the 3d sublevel, right? So again, we're talking about iron. Right now we're at 4s. Iron's right here. We don't jump immediately over to this p block. You guys just have to recall that we attend to electrons that get filled in this 3D sublevel, okay? So nothing particularly new as far as transition metal electron configurations go. The one reason I wanted to discuss it is because there are some exceptions that your book touches on. Imagine a scenario where we have chromium, right? It may be that this is the anticipated or predicted electron configuration for chromium. In fact, we find that it's a real electron configuration actually terminates in 4s1 3d5. And one of these electrons actually got filled into a d orbital instead. The reason behind this, we're not going to go into it much. The idea is that by having half-filled d subshells here, there's actually a stability that's conferred upon that atom, upon chromium. Okay, but again, there's even kind of some debate there. I just wanted to point out that there are some exceptions among these transition metals. And in fact, we find another very common exception in copper, an element we'll be dealing with quite a bit this year. Again, the anticipated electron configuration maybe culminates in that 4s2 3d9. We find it's wrong. One of the electrons, again, actually kind of leaves that s orbital, ends up in a d orbital. The idea here being is that by having this kind of end to our electron configuration, there's a stability that is conferred upon having this, completely filled d sublevel there. Okay. Bottom line is, if you want to kind of commit, chromium and copper to memory, that's great. There's a lot of exceptions among the transition metals. Why those exceptions kind of exist, again, there is some debate there. So just realize that they exist. Be familiar. I'm not going to hold you super accountable on these things. Okay. That being said, most of our transition metal electron configurations, pretty straightforward. Okay. When it comes to positive ion formation, I think the big rule is that we just need to remember to remove electrons in the highest energy level possible. Right? So when it comes to something like potassium, obviously we're going to remove that single valence electron in the 4s level there. Knock this thing down, where it terminates with just the 8 valence electrons here. We got the nice stable noble gas electron configuration. We get that potassium +1 cation there. So again, kind of a review from honors. That being said, there are some positive ions that are a little peculiar, okay? And we encounter that when we get to the transition metals. So the big rule is exactly the same as we just stated it. We will always remove electrons from the highest n level first. The reason transition metals are a little weird is because we have d orbitals kind of in the mix now. So we will remove electrons from an s orbital in the highest energy level first, and then we will remove d electrons from the energy level that is immediately before it. Okay, and we're going to see some examples here. Okay, now if p orbitals come into the mix, we'll see a nice example there as well. So let's say we have iron, and this would be its abbreviated noble gas electron configuration. So nothing too weird with iron. We find that we fill the s orbital before we fill the d orbital. Okay. When we go to ionize iron, say the ferrous version here, the 2 electrons we are going to remove are the ones from that s orbital. Okay. The reason behind that is because they are in the highest energy level. So those get removed. From there, if we want to form the ferric version, the 3+ version, then we're going to remove the remaining electron from that d subshell there. The reason I'm bringing this up is because this is a little counterintuitive, right? If we were to start kind of by filling an electron filling up an atom per the off-ball principle, say we're constructing an electron configuration from the ground up, we always fill s, then d. Right? But when it comes to removing electrons, we're actually going to remove electrons from the s orbital first. Just a side note here, keep in mind that these two are not isoelectronic. While they're both ions of iron, they do differ in their total number of electrons. Just to kind of tidy that up a little bit, imagine we have our neutral lead atom. Okay, we have its abbreviated noble gas electron configuration here. When it comes to forming the Plumbic, or the +4 version there, the first thing we're going to do is remove these 2 electrons in the p orbital here. The reason behind that is because the highest energy level is the 6th energy level, and these p electrons are going to be a little bit higher in energy than these s electrons here. Okay, so the first 2 that get removed are these right here. Boom, gone. Okay, and in fact, we would have just formed Plumbis, or the Pb2+ version. But because we're dealing with Plumbic, or the 4+, we need to remove an additional 2 electrons. So still in the 6th energy level, but again, the s being slightly lower in energy than the p, we will furthermore remove those 2 electrons. So the complete electron configuration for the Plumbic, or 4+ ion of lead, is Xe, 4f14, 5d10. Okay, so we are always removing electrons from the highest energy level first. And again, things just get kind of a little counterintuitive as far as our transition metals there go. Okay, the last thing I want to discuss is the concept of diamagnetism and paramagnetism. This is pretty simple to digest. As far as diamagnetism goes, bottom line is these different atoms, or these ions, do not contain any unpaired spins or unpaired electrons. And as a result, we find that they are actually slightly repelled by a magnet. We're going to get into paramagnetism here in a second to kind of firm up that last statement. But because I have no unpaired electrons, I have no unpaired spins, we would expect that the atom of neon here would actually be slightly repelled by a magnet. In contrast to diamagnetism, paramagnetism does have a net of unpaired spins. Okay, and as a result, there is a slight attraction that we're feeling as far as a magnet goes. Okay, as far as unpaired spins, unpaired electrons, we just need 1 or more. And again, we're going to see that here in a moment. Okay. When it comes to lithium, which only has 3 electrons, we fill up the 1s level first, then we go to the 2s. Here's the single unpaired electron, And as a result of having just kind of an uneven number of electrons, this unpaired electron here, we would expect that this would be attracted to a magnet. We find the same thing in our neutral atom of iron. I just kind of, instead of the electron configuration, I wrote out the orbital diagram here, and we find that there are 4 unpaired electrons. So whether there's 1, whether there's 4, bottom line is we just need 1 or more. And we would expect, again, that the neutral atom of iron there would be attracted by a magnet. We find the same 2 things kind of going on here as in addition to the or I should say along with the ferrous and the ferric forms. When we go to remove 2 electrons, again, we're going to remove them from the highest energy level first, so they'd be coming from this 4s level. So those get removed away. We're left with 6 electrons remaining in the 3d level. Again, 4 unpaired electrons. We knock out 1 more. This electron went away in order to form this final electron configuration for Fe3+, where now we have 5 unpaired electrons. And as a result, we would deem Fe3+ as paramagnetic, and we would expect there to be an attraction to a magnet. Thanks, guys.